I'm Patrick Henriksen, and I'll be presenting our paper Repairing Misclassifications in Neural Networks using limited data. The work here was done by me, Francesco Leofante, and Alessio Lumoscio, all based at Imperial College London. So, we all know that neural networks have exhibited a great performance on a wide variety of classification tasks. And that's exemplified here with a input from the MNIST digit dataset, a handwritten 8, and then a neural network that classifies this 8 correctly as a number 8. However, despite being trained to high accuracies, neural networks can still make mistakes. This is exemplified here by a common mistake in the MNIST digit dataset, where we have a 7 as an input, and then the neural network classifies it as a 1. So the question we try to explore in this paper is, can we modify the network such that misclassifications are removed? And more formally, we assume that we have a neural network N and two sets of input R and C. N misclassifies all inputs in R while correctly classifying all inputs in C. Typically here, R would be a set of points that we found misclassified by the neural network, and often a set of points of special interest. So there's an underlying assumption that R is more important than the overall performance of the neural network. C, on the other hand, can be, for example, a subset of the training dataset that is classified correctly. Now, having these, the question becomes how to repair the neural network N against the repair set R without altering its performance on the correct set C. Unfortunately, in the paper we show that this is not possible in the general case for a fixed network architecture. So what we need instead is a heuristic that can repair N on R while minimizing the impact on C. Secondly, we also consider what happens when we do not have access to the full training data. So there are some key differences compared to retraining here. First of all, it's the minimality of changes. Retraining a network from scratch may result in a completely different network with new bugs. Repair, on the other hand, focuses on targeted changes. So repair attempts to repair the misclassifications in R without affecting the overall network performance otherwise. Secondly, we have the data availability issue. Retraining from scratch is only viable when lots of data is available. However, repair, as we consider it in this paper, can be applied when data is scarce. So before we go on, we want to discuss a little bit about minimality of repair and exactly what we mean by minimality. Much previous work on repair considered minimal changes to the weights of N such that R is fixed. And the underlying assumption here is that making minimal changes to weights also has a minimal impact on the network performance overall. However, the assumption above is not true in general, because, for example, accuracy may be severely affected by making small modification to weights. So what we do here instead is that we introduce a new notion of minimality in repair. Specifically, we want to modify the weights of N such that R is repaired and accuracy drops on C are minimized. And remember that we often consider R to be of a particular importance, thus some accuracy drops on C may be acceptable. However, we want to minimize the overall impact here. So how do we do this? We measure how change of a weight in N influences classifications on R and C. Then we only modify the most promising candidates. And we'll go a little bit more into detail on that now. So we use, as I mentioned, influence to measure how changing a weight may affect the output of the neural network N. And the influence measure we use is basically the ratio of gradients with respect to R and C. So we evaluate the gradients of each weight with respect to R, then the gradients of each weight with respect to C, and we use this to identify good repair candidates. And good repair candidates here would have a large influence on inputs in R and a small influence on inputs in C, such that hopefully modifying those weights will quickly help classify inputs in R correctly, while small modifications to those weights will not have a huge impact on inputs in C. Next step, we use this influence measure in iRepair, an algorithm we propose to repair neural networks. So to reiterate a little bit, the algorithm takes as input a set R of misclassified points. And remember that we often assume that these misclassified points are of particular interest. In this case, we illustrated with inputs from the number 7 in MNIST, but in real-life scenarios, this might, for example, be in a self-driving car, where classifying stop signs might be of a higher importance than classifying more informative street signs. Next, we take as input a correct set C, which here works as a proxy for the overall network performance. We then use these two sets to evaluate the gradients with respect to some loss function, and then we consider the ratio of the gradients for each weight with respect to R and C. And the key idea is to only modify the weights with the best influential ratio and keep all other weights frozen. So if the ratio of the gradients with respect to R and C is high, then we modify those weights during backpropagation. If the ratio is low, on the other hand, then we freeze the weights. After determining which weights to freeze, we repeat backpropagation on R and C until all points in R are correctly classified. Finally, we evaluated iRepair experimentally in 4 different scenarios. These scenarios were designed to answer 4 questions. First of which, is iRepair successful in repairing misclassifications? Which is obviously one of the most important questions to answer. Secondly, is our influence measure informative? So does it actually aid in repairing? Question 3, does iRepair cause overfitting? And finally, is our minimality criterion effective? For question 1, is iRepair successful in repairing misclassifications? We generally found that for small correct sets, iRepair was able to repair all points in the repair set. However, the second part of this question is what kind of influence we actually have on the overall network performance. To evaluate this, we compared iRepair with retraining on a CFAR10 network, and we ran repair experiments for various sizes of R and C. Then we recorded the accuracy drops for each run. The accuracy drops here are measured on an extra validation set that's unseen during training and repair. In the plot on the right-hand side here, we see the accuracy change on the y-axis and the size of the repair sets on the x-axis. What we clearly see here is that the results for iRepair, marked in blue with confidence intervals, outperform the results for retraining for repair sets of all sizes tested here. Thus, iRepair has a higher repair success rate and results in better accuracy than retraining. Question 2. Is our influence measure informative? To evaluate this, we analyzed the extent to which influence affects the results of iRepair. We did this by comparing with a baseline strategy where weights in the network are locked with a probability of p instead of locking the most influential nodes. We then analyzed the resulting accuracy drops on CFR10 by running the repair algorithm with this locking strategy. On the right-hand side here, we see box plots of the accuracy changes for iRepair and various locking probabilities. We see that for locking probabilities between 10 and 90%, the performance of the repair algorithm is actually very similar. So it doesn't seem to be very important how many random nodes are locked. However, we clearly see that locking with a random probability results in much worse results than locking with the influence estimation of iRepair. So in conclusion, influence results in considerably lower accuracy drops than randomly locking nodes. Question 3. Does iRepair cause overfitting? Misclassified inputs are successfully repaired by iRepair. However, due to the stopping condition of iRepair, which is stop as soon as all repair inputs are correctly classified, these repairs may be brittle. Theoretically, the repaired inputs can lie very close to decision boundaries and thus may not generalize very well. To deal with this, we also attempted to enforce a minimum margin during repairs such that classifications become more robust. And by margin here, we mean the confidence for the correct class, or the difference between the confidence for the correct class and the confidence for the second biggest output. On the right-hand side here, we see a plot of the results for a wide range of margins. And interestingly, what we see here is that enforcing larger margins actually doesn't lead to a significantly larger accuracy drop. Moreover, we see that for all the margins, iRepair outperforms retraining by a similar amount in the average accuracy drop. Thus, more robust repairs, in the sense of having larger margins, can be enforced while only causing small accuracy drops. And for a final question, is our minimality criterion effective? To evaluate this, we compared with retraining and a state-of-the-art repair approach using minimal modification, or heuristic. The heuristic here considers minimal modifications to be minimal absolute changes in the weights. is completely data-free, so it's not directly comparable, but it's still good to illustrate the difference between the minimality criterions here. We analyzed the accuracy drop listed under D in the table on the right-hand side and the time taken to repair listed under S. What we see from the table is that both retraining and repair lead to significantly larger accuracy drops than iRepair for various hyperparameters. In particular, with a large gamma, so a large amount of nodes being locked by iRepair, we see that we often have accuracy drops around 10 times better than the comparable algorithms. We also interestingly see that iRepair succeeds in repairing significantly faster than the comparable algorithms. Finally, we note that while in most cases all points were repaired, repair was somewhat influenced by a epsilon hyperparameter here, which was the maximum allowed change to the weights in the network, and with too small a epsilon, some of the repairs marked with a star here failed. So in conclusion, the minimality condition of iRepair outperforms both retraining and repair. So in conclusion, Neural networks are powerful, yet they may fail sometimes. Repair tries to remove failure cases without disrupting the overall network performance. Often we also assume that the repair set is somehow more important than the overall network performance, thus sometimes we accept a slight reduction of the overall network performance as long as the repair set is repaired. Exact repair or repair with guarantees may not be possible in the general case. Therefore, heuristic approaches are needed. We here proposed an influence heuristic to find weights that minimize the impact of repair operations. We then used this influence heuristic in iRepair, an algorithm to repair neural networks. Finally, we experimentally showed that iRepair beats retraining and state-of-the-art repair approaches. In future work, we would find it interesting to see whether iRepair can be used to improve the general robustness of neural networks. For example, by using iRepair to repair sets of adversarial examples. That's all we had. Thank you for listening to our presentation.